Okay, so a year into lockdown and I'm reduced to just a pair of giant hands on a screen. That's all that's left of me. This is actually a set of videos, or at least the first video, or a video, on something I've been on and off doing for ages and chasing my own tail and getting nowhere. It's a synthesizer, and it's gone through various forms and ideas, and I've reached a stage where I've got something to put in a video. So here's the test circuit, crudely put together on breadboards, and the basic design philosophy of it, I'm going to go into that probably in the next video in more detail, but the basic idea is to have it run off a PIC microcontroller, which is this. It's the heart of the beast. It's a PIC 167, no it's not, it's a PIC 1777, which is absolutely packed with peripherals, analog peripherals. It's got 4 10-bit digital to analog converters, 4 5-bit ones. It's got 3 16-bit timers, 4 16-bit pulse width modulators, some 10-bit pulse width modulators. It's got, and 4 operational amplifiers on board as well, all of which means you can build most of a semi-analog synth on a chip. Now, it's not a super high power type processor that you do synth modeling on. That's not the purpose of it. It will be a hybrid of digital analog. The oscillators are all running on here, and they will be effectively digital, and that gives me a lot of options on what they do. The filter's completely analog, and then the VCA is effectively digital. It runs through a DAC. Now, I'm actually going to do this first video mainly about the filter, because I started off doing, well, I'll do the oscillators and the VCA. They're the sort of easy bits, and I'll worry about the filter later. Then I realised the filter was the main thing for worrying about peripherals with, and then started chasing my tail with it. Let's just prove it works, by the way. I've got it connected up to a MIDI keyboard. Oh, you can see the gate going on and off here. That was something not very tuneful. The oscillators, well, I'll get back to them. This is the microcontroller, as I said. This is just the MIDI input, which is read by the microcontroller. Up there you can see the programming connections for the microcontroller. There's also, this board isn't really part of it, it's just a board I built ages ago that produces buffered voltages from these pots and switches, and has an LED, and I use it all the time. There's also a serial port I can hook in up there for getting, oh dear, we lost that. A serial port up there for connecting up to get numbers out of it. This board has the current filter on it, and it was with the filter where I've chased my tail somewhat and then come up with a solution I'm really pleased with and even a bit proud of, and that's why I decided to make the first video about the filter. So as I said, at the moment we have some notes coming out. Now the oscillator is pretty basic, and in fact, let's have a look at the output of it. This is a oscilloscope type program on the computer, so you can see the output. That's a square wave, well, it's a pulse wave. You can pulse width modulate it like that. You can also change the slope, which allows you to get a triangle out of it, and you can change that to become a sawtooth. None of this is quite working properly at the moment, it's all a bit glitchy. because it's just running test code at the moment, and the VCA is simply gating at the moment. There's no envelope on it, but that's the basic. You can see it running. I'm using a slightly ropey PC oscilloscope thing because it's difficult to film my main oscilloscope at the same time. So anyway, to backtrack, the basic idea is a monophonic synthesizer. That is, it has one voice, or that it has multiple oscillators. But I want something. The idea is to make it as absolutely simple as possible, because I've been contemplating this in various forms for quite some time, and always ended up starting to produce things that were too complicated and that I was never going to finish. I want something that's the design philosophy is that it's little more than a microcontroller. Now, of course, one is a bit limited in how far you can go with that sort of philosophy in reality. Oh dear. That's a bit better, isn't it? But most of these gubbins, this is actually, there's two filters here. The first one is the failed version, which I failed with, in that it didn't suit well, it worked, but it wasn't right. The second one is this one, which I'm going to get onto in a moment, and I'll just show it working actually. Let's go back up to the oscilloscope. I'm having to switch lights on and off because of reflections. Now, what I can do is turn the filter down, and you can see on this is the spectrum analyzer, and you can see it's cutting off lower and lower like that, and you have a resonance which you can see coming up here. That's the resonant peak there, and eventually it goes into self-oscillation. If you're wearing headphones, be careful now. You can see it cutting off a bit up here. Like that. So one of the key constraints with this idea is that because it's a microcontroller, it runs on 5 volts. So everything has to run on 0 to 5 volts, 5 to 0 volts. Can't have dual rails, and they can't be higher than 5 volts. Now, most analog synthesizers and all the Euro rack stuff tends to run on plus and minus 12 volts, which is useless for interfacing to microcontrollers. So that's out. And that means that external circuits like filters, you have to think a bit harder. The original plan was a cunning plan, and the idea was this. Basically, this is a standard filter. You can see on here it's called a Salon and Key filter, and you may be familiar with it. It's 12 decibels per octave, which means it has 2 filter stages, and all you need to do to make it work is vary these resistors. Now, you could just use a potentiometer, a variable resistor, to do that, but the problem with that is that then you can't control it from outside. So I thought, I'll use the digital to analog converters on the microcontroller, because they're just a string of resistors. So as you turn them up and down, they basically are acting as variable resistors. And I pursued that for a week or two, but I found a major problem which I hadn't realised before. They have a high output resistance, regardless of where the potentiometer is set. There's about an extra 80 kilo ohms on them. That means that because the resistor chain itself is only about 400k, you can't get more than about 2 octaves of variation out of it, and you actually need the filter to go many more octaves than that. So then I started thinking about all sorts of complicated means of switching extra resistors in, or switching capacitors in with analog switches in series or parallel with these capacitors or these resistors, and it all got terribly complicated. So then I started looking around for another filter, and at that point I found this. This is called a Steiner filter, or a Steiner-Parker filter, and it's quite popular with synthesizer hobbyists or builders. And if you're aware of the Mini Brute, that uses a Steiner-Parker filter, and I think it's the cleverest bloody thing I've ever seen. It's all based on this diode ladder here, or diode chain, and how it works is that diodes don't just switch on and off. When they're switching on, basically they vary their resistance, and then when they're fully switched on, they stop varying their resistance, but over a fairly small range of between about 0.3 and 0.6 volts, the resistance changes. So what the Steiner filter does is it puts a DC biasing voltage in to the chain, and then overlays on that the analog. I ought to draw this, really. Let's draw this. No, let's not draw this. So the bigger the biasing voltage, the lower the resistance goes, until and so that interacts with the capacitors. Problem is, this uses what's called a long tail pair, these two transistors here, and there's a few problems with that. Firstly, you need to get really well matched transistors. They need to be very, very similar characteristics, and it all varies with temperature, an enormous amount. And this is why one of the reasons early analog synths were so unstable was transistors heating up, just normally heating up with the temperature changing. The second problem is you need quite a lot of volts here in order to create a current sink. See, this is connected to minus 10 volts here, and it goes through a resistor, and that acts as a current sink. Well, I've only got 5 volts to play with, and I'm losing 1.2 volts across there, and then I've got my 0.6s in the diode chain. There isn't a lot left. There aren't many volts left for me to play with, and I didn't want to get fiddling around with matched pairs of resistors. So then I thought, well, in fact, all that this is doing is making sure that the control voltage, which is coming in here, that the control voltage is balanced. You've got the positive control voltage on this side and the negative control voltage on this side. So I came up with something else, and I'm going to have to switch to a piece of paper now, which is this. Oh, no, I don't want to do that. So instead of using a differential pair, this just uses 2 operational amplifiers. I presume that the first one is already inside the whatever's generating a control voltage. The second one inverts that. So this goes from 2.5 volts up to 5 volts, and this goes from 2.5 volts down to 0 volts, because they're pivoting around the central 2.5 volts of my supply, and that will bias the chain. Op amps are completely stable. You don't have to match them because they're already matched. They don't vary with temperature all that much. They're just very, very stable. So we've got an inverting op amp here doing the same thing. And the rest of the circuit is basically the same. This is another op amp which just acts as the amplifier for the circuit, and that does the same as these transistors did on the original 1974 version. And I think he just used transistors because you know, op amps were not particularly, I think the earliest ones were out then, the 709 and maybe the 741, but yeah, the 741 was out, but they weren't widely used. Whereas nowadays we've got 50 years more technology on top of that. Otherwise it works just the same. And after all the fannying about with the supposedly clever idea about using the digital to analog converters, this just worked like a dream. It worked first time, and I love the sound of it. And let's hear it again. This is the filter cutoff here, and you can see on the circuit board, this is the operational amplifiers. They are actually these capacitors here. The I've used 1 nanofarad. I might go a bit higher, but one's pretty good. It goes way up above the audio range. These are currently going up to about 25 kilohertz, so I could probably use 2.2, something like that. And the diode string is here. Other than that, it's just a couple of resistors, which are these resistors. Just make sure this one, sorry, no, yep, this is the signal coming in here. Let's just turn that off. This is the signal coming in here, and it goes in via high value resistors, so it's small compared to the bias, and then it gets magnified up by the amplifier. And I think I forgot to mention the reason for this being a positive and a negative control voltage is so they cancel out. The voltage tapped off the middle is exactly in the middle of the two, so it cancels out. And the only thing present at that middle point is going to be the sound voltage, which is being affected by the changing resistance of the diodes. I think it's incredibly clever, and it was invented, I forgot to say this, by this guy Niall Steiner, who you can still find on YouTube, who appears to be a bit of a genius and has recently been revived. It's an incredibly clever idea. I wish I'd thought of it, but I'm not clever enough. So here again is the Steiner filter. So anyway, the next stage is, I think I'm ready now to build the first circuit board, and the hope is that these will be really small, almost like what was the saying, jelly bean. And that's one of the reasons I want to keep the external part count down. These PIC microcontrollers, these are under £2, and that's buying in like quantities under of sort of 5 or whatever. I wanted to avoid using expensive external components like digital to analog converters and so on. The only slight cost penalty is that because of the 0 to 5 volt supply, I'm forced to use rail-to-rail op-amps, which are more expensive. That is op-amps that can go down to 0 and all the way up to their voltage rails. Other than that, I think I'm going to knock up the first actual one on strip board, and then the large part of it is programming. At the moment, the programming is, as I said, really basic. Sorry, I just like the sound of that. The programming is basic, and I kind of stopped programming until I got a clearer idea of how the whole thing works. Where it goes from here, I don't know, but I thought I would post a video anyway about it, and there it was. And if you're interested in seeing more about the synthesizer, please like the video and subscribe, hit the bell, and leave a comment, especially about the filter. I'm interested in people's reactions to the swap from using a differential pair to a pair of op-amps. Okay, that's it.